this, as seen in the fantastic software GeoGebra, is a three-dimensional representation of Newton's law of gravitation. On the left here we have what do we have? We have an equation z equals c times d times x over y squared. So in this equation, our y represented by where are we? That would be represented by our green, I suppose you call it, green line, green, yeah, sure, we'll call it green axis along here. That is our, well, the distance between the center of mass of two objects. Our red line represents, what would that represent? Represents the mass of our object, and well, c is just a constant. In real life, it would be 6.67 times 10 to the negative 11, but that's not going to produce a very interesting plot, so we've expanded that for viewing purposes. It wouldn't change the shape. It would just, well, it would change a bit of the shape. It would just, this is how it looks. This is how it looks, basically, essentially. Look, I'll move through some of these dials. It'll pinch the surface a little, so that'll expand a bit. You can see it on the top end. That'll, I mean, essentially it does the same thing as the x would as well, if the x was a constant that I could move. Yes, this is the general shape. So yeah, this is what Newton's law of gravitation looks like in 3D. Obviously, if we look from the 0 point in the middle here to the right, none of these numbers really make any sense unless you have an object that has negative mass, which, as far as we know, doesn't exist. But yeah, you never know. Well. I mean, there are arguments to make that the universe itself has negative mass, but that is beyond the scope of this small little, cacophony of madness that I'm showing now. But yeah, this is what it looks like. Interesting points. So as we get closer and closer to the central radii, it'll be basically when the green gets closer and closer to 0, our objects get the force increases until there would be some point at which, if we can zoom out far enough, well, yeah, this is, if we could zoom out far enough, as in if we could zoom out infinitely, then we would eventually find where these 2 points here and here would converge. Essentially, that meaning that the two objects have collided. Obviously, when they collide, if their center of masses combine, you don't have some moment of infinite force. This is the limitation on Newtonian mechanics. And yeah, I mean, it's not that Einsteinian mechanics has it's not like it drops this limitation entirely. There are infinities that pop up. Black holes is the popular thing, but again, too expansive for this little demonstration. Yeah, lovely little equation, and yeah, it's pretty simple. So yeah, I should also mention that D is our second object. So, quick explanation: now that we've looked at the shape and gone, ooh, pretty. Z is our force. So F. So the general form of the equation is, or the way it's written is F equal G m1 m2 on R squared. Here Z is F, or our gravitational force, or our kilograms meters per second squared. C is our constant, as I mentioned, 6.67 times 10 to the negative 11, or 1.3 here. D would be our, let's say our M1 or M2, whichever, doesn't really matter. Basically, D would be one of the masses, and X would be another of the masses. So the thing about D here is D can be considered a constant. We could imagine here setting D to be something like, I don't know, a star, and X would be our position along the red line, being I don't know, maybe a planet or something like that. It doesn't really matter. It's two objects. It doesn't matter what objects you have. Fortunately, we can't view things in 4 dimensions. If we could, then I could kind of make this a lot more applicable to the universal law of gravitation. I could enter D in as a variable, but it's not applicable here. There are other forms I could do this in, but anyway, it's again beyond the scope at this point. And yeah, y is just the distance between 2 points. So yeah, that's pretty much it. There's nothing else. I'm really just rambling at this point. But yeah, it's really fairly simple. And again, really, only if we're looking here at this angle, it's the top left of the plot that really confers to reality. So everything above the green line and to the left of the red line, everything else, I mean, there are some theoretical ideas about, so it's, in a sense, we've divided physics into 4 areas. Top left is known, understood, pretty comfortable stuff. The top right would be objects of negative separation, which is really just the same as objects of positive separation. The mathematics comes out the same. It's just kind of, it's an artifact of the mathematics, really. So, I mean, maybe there's some kind of context or some kind of, stretched out way you can think of the universe. Use that to kind of picture something, but for practical purposes, left and the right here are the same thing. Down the bottom and down this side, as I mentioned, is where we get to say some unrealistic physics, or at least physics that we don't see this in the universe, right? So if we had objects of negative mass under Newtonian physics, what we see here is that we have a negative force. We can interpret this as, say, for instance, a force pushing the objects away from each other. Our force would, essentially we can imagine our force vectors pointing away from each other. So objects of negative mass would hence have negative gravity, and the closer you push them together, the more, the further apart they get pushed. So as our, here we go. So imagine we're on this side, the bottom side here, and as our objects get closer and closer, as our x mass, y is the distance. So yes, as our objects get closer and closer together, moving closer and closer to that red line across the green line, the objects start to push against each other with more and more force. I guess essentially, this could be thought of as, I mean, there are things that repulse each other in physics. So, magnets, if we were to push two north poles together, this might describe their repulsion. Off the top of my head, I can't remember whether or not it's a square law for magnets in this case. Well, I mean, it wouldn't be a square. It wouldn't necessarily be a square law, or at least the repulsion you would see is dependent on the impinging angle of the two objects. And it's depending on a lot of things. So it's not as simple as thing pushes away. Because luckily for us, or maybe unluckily, who knows, there are no magnetic monopoles. So, which again, another video. But yeah, I don't know. I just wanted to kind of ramble on about a cool little physics thing.